everybody. Mrs. Bixler here, and we are starting Unit 8, which is our second to last unit of the year. Woohoo! And Unit 8 is all about circles. You will see how much I love circles this unit. They're really cool, and there's a whole bunch of stuff that can happen inside of them, and it rivals my excitement, I think, for right triangles. All right, so when we think about a circle, right, we usually think about just something that looks like this, right? We all have known circles for a long time. But if we had to define what a circle is the set of points that are all equidistant from a common point. So here's a common point, and I know that there's a point here that is a certain distance from that point. But technically, there are an infinite number of points that are this same distance from this red point. So I could draw a little line here, I could draw another one here, I could draw another one here, right? So there are an infinite number of points. The connection between those points, just pretend this is perfect, not perfect, looks like an oval. That set is what a circle is. So here are the important things here. This point right here is what we call the center. And then these little line segments here from the center to the point on the circle, this is what we call the radius. And you know about radii. You've been talking about radii for a long time. And you've also probably talked about diameters. So a radius is always going to be, like I said before, it's going to be the line segment from the center to a point on the circle. All radii within a circle are congruent, which makes sense. All radii are always going to be congruent. And then the diameter, so here's our radius. And then the diameter, we always think of a diameter as twice the radius, right? So I know that my radius is from here to here, but then my diameter keeps going. So it's essentially 2 radii. Great. And that's usually like typically our first thoughts in terms of what a diameter is. All right, so now I'm going to hit you with some vocabulary that is new, probably for some of you. All right, so a chord within a circle is simply a line segment whose endpoints are on the circle. That's what a chord is. A secant is a line or a line segment that contains a chord. So a secant could be something that looks like this. Again, this could be a line, it could be a line segment, but all that matters is that it contains a chord. And the last one is a tangent. And so a tangent is a line or a line segment that touches the circle in only one point. And this is what we call the point of tangency. We'll talk a little bit more about tangents in the next section. So again, a chord, a secant, and a tangent. Those are 3 new terms. So now, knowing these new terms, how do you think you could define a diameter? So before we said a diameter was just twice the radius. But now I know that a diameter touches the 2 sort of extreme ends, right, of ends of a circle. So a diameter is going to be a chord that goes through the center of my circle. Good. See why that makes sense? Awesome. Also still twice the radius, but now we know we can use this new vocabulary word of a chord that goes through the center. Great. So a couple little things I'm just going to throw at you, just some definitions and some concepts that I want to make sure you're comfortable with. If I talk about congruent circles have congruent radii. So the radii, the lengths of the radii are the same. Concentric circles are 2 circles that have the same center. So this bigger circle has this purple center, and the smaller one also has that purple center. So congruent circles, same radii, concentric circles, same center. Another little thing that is important is something called an inscribed polygon and a circumscribed polygon. So an inscribed polygon, and it sort of makes sense, an inscribed polygon is when all of the sides of the polygon are within the circle. So essentially, it's a polygon that is made up of chords. Woohoo! Now, a circumscribed polygon is a polygon that goes around a circle. So if you think of like circumnavigate, right? You go around that circle. And so here, my sides touch in only one spot. So a circumscribed polygon is made up of tangents. Pretty cool, right? All right, so inscribed, circumscribed. Make sure you know those and you feel good about those. All right, so here's a little question for you. So this is kind of new, this guy. When you see this symbol, that means circle. So it's a circle with a center in it. So in this case, they're saying given circle Q and the measurement of angle AQB equals 60 degrees, I want to know what line segment AB is. What's the length of line segment AB? I want you to pause the video and just try this one. All right, we're back. So the measurement of this angle is 60 degrees. And we are interested in this line segment. So what nice little shape do I have here? A triangle, exactly. So I've got a triangle, but even more importantly, what kind of triangle is it? It's an isosceles triangle, right? So I know the two sides are congruent to each other. These are the radii. So if I know sides are congruent, I know the base angles are congruent. Wait a second, this is more than just an isosceles triangle. This is an equilateral triangle because if this vertex angle is 60 degrees, what's left is 120. But if those two have to be congruent to each other, then they're all going to be 60. So this is a nice little equilateral triangle, which means side length of AB is 20. Hopefully you got that right. I know it's tricky, but you're going to start to see shapes within triangle or within circles, which is kind of cool. All right. So I told you that we were going to be talking a little bit more about tangents. So this is section 9.2, and it's all about tangents. So section 9.2 talks about how if we have a line or a line segment that is tangent to a circle, it just means that this line that we have right here, and I'm going to make it look a little bit more exciting, very exciting. Remember, a tangent is touching a circle in one spot. And so what we are able to do is, remember, there are an infinite number of radii within a circle. So I can draw a radius from the center to that point of tangency. So remember, we call this little guy the point of tangency. So I've just drawn a radius that is now perpendicular to the tangent. So always, 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 a tangent will be perpendicular to a radius. I can draw a radius that is perpendicular to that tangent within the circle. So remember, there are an infinite number of radii, so we can always, always, always draw one that's perpendicular. And it's kind of cool when you start to see problems like this. Pause the video and try and answer it. All right, we're back. So if I know that OT is tangent to circle R, there's my little right triangle. I know that OR is 6. I know that OT is 8. Snooze, give me something harder. You should have been able to figure out that RT is 10. Awesome, 6, 8, 10 triangle. Multiple to 3, 4, 5. Fabulous. The little bit harder thing is figuring out what AT is. Now remember, if this whole thing is 10, don't forget that all radii are congruent. So RO is a radius, but RA is also a radius. That is also 6. So it means that AT has to be 4. Yeah. All right, good job. Scooching on. So here's a little corollary, and a corollary is just like a side note, right? So remember, tangents are always going to be touching a circle in one spot. If I have two tangents that come from the same point outside the circle, they are congruent to each other. And here is why. I know that this radius and this radius are congruent. I know that they make little right triangles here. Watch this. I have just now created two right triangles. Do you see them? I know that this guy is congruent to itself because of the reflexive. So look what I've got here. two triangles that are congruent because of HL. See that? See the hypotenuse is this green line, the reflexive one, and then the legs are going to be our radii. And so I know that these two triangles are congruent to each other. Thus, because of CPCTC, I know that this tangent and this tangent are going to be congruent. So always, always, always tangents to a circle from one common point are going to be congruent to each other. All right, last section. So section 9.3 is all about arcs and central angles. And we've actually talked about central angles already without even really realizing it. So when I talk about an arc, I'm talking about a piece of a circle that's on the outside. So remember we talked about like all those infinite points. So it's essentially all those infinite points, but it's just a piece of it. This is what we'd consider a minor arc. So I'd say a minor arc, AC, and watch. This means the length of line segment AC. This means line segment AC, which would be that. I don't want that. No way, Jose. So here's what's kind of cool. You would call this arc AC. How cute is that? Arc AC. Amazing. And then we've got a major arc here as well. Now, a major arc would be the bigger one. And you'll see that we're usually going to be talking about minor arcs. But if I have a major arc here, if I call this arc AC as well, because technically it is, right? A to C, it gets confusing because I don't know which one you're talking about. So usually you would add in a letter like that. So I would call this arc A, D, C, and you just put the arc over both of them. Cool. All right. So now we have yet to talk about a central angle. So a central angle is essentially what makes up that arc. So here we were talking about our arc AC, but right here, this angle, angle ABC, that is what sort of forms that arc AC. So if I have a central angle here, and in this situation, I'm calling it angle X, and I want to talk about the measurement of arc AC. So I've got a little measurement of arc AC here. The measurement of arc AC is going to be equal to the measurement of that central angle. So the measurement of an arc is always equal to the measurement of the central angle. Always, always, always. What do you think the maximum measurement of an arc can be? 360 degrees, exactly, because if you went all the way around, it would be 360 degrees. And same thing for the central angle, right? Fab. But I want you to note that the measurement of an arc is different than an arc length. So in this situation, let's say that all of these central angles were 30 degrees. That means the measurement of all of these arcs would also be 30 degrees, right? Because the central angle is equal to the measurement of the arc. But would you see here, would you agree that if I were to take like a piece of rope or something and I were to put that on across this arc, like this guy, and then this guy, and then this guy, and I would just straighten them out, do you see how each one of those would be different? The orange circle is the greatest circle. And so that arc length is actually going to be longer. So arc measure is different than arc length. And that's a really important distinction. Right now, we're talking mostly about arc measure. Arc length will come up later. But it's important to note that arc measure is what we're talking about here. And really, there's a restriction with arc measure, right? The biggest it can get is 360 degrees. But arc length is infinite because I could have a circle that's enormous, and I could have an arc length that's also enormous. All right. So one little question here. I want you to pause the video and try and find the measurement of angle 1. All right, we're back. So easy peasy. Hopefully you figured this one out. The measurement of angle 1 is 72 degrees. Snooze. Awesome. All right, this next one, on the red one on the upper right, the measurement of angle 1 is 95 degrees. Just had to do a little addition and then subtract from 360. Ooh, this one's kind of nice. The measurement of angle 1 is 150 degrees. And then let's try this black one. So the black one is 50 degrees. Now the reason why this is the case is got little vertical angles, right? So I know the measurement of this arc is 130. That means this central angle has to be 130. This guy over here also has to be 130. So that means this arc has to be 130 degrees. And I know the full circle has got to be 360. So I'm 100 short. This guy's got to be 50. And this guy also has to be 50 because we've got another set, right, of vertical angles here too. Cool. All right. So two last little things. So we're looking at circle B here. And I'm telling you right now that A, B, and D are collinear. B is between A and D. B is also the center of my circle, right? If I'm calling it circle B. So this is what we call a semicircle. And so what do you think the measurement of arc AD is going to be? What is this measurement going to be? Pause the video and then come back. I hope you said 180 degrees. You would be right. Yes. A semicircle is half the circle. So if I know 360 is a full circle, then I know half of it's got to be 180. All right. Last little question or last little slide I wanted to make sure we talked about. So we talked about adjacent angles before, but now I want to talk about adjacent arcs. And this is a super simple concept. Let's say that I've got arc BD here. So here's my arc BD. And then I've got arc DQ. The angle, or sorry, the arc addition postulate is just like the angle addition postulate. I know that arc BD plus arc DQ is equal to the larger arc PQ. Cool? And so, which makes sense, right? These smaller pieces add up to a larger one. And this isn't a proofs unit, so you're not going to be using this, in a 2-column proof. But this concept is important. All right, so that's it for me. Go ahead, tackle the homework, and I'll see you soon. Thanks.